This is Dr.S.Prasanna, Assistant Professor of Mathematics in Pingle Government College for Women, Warangal. In the previous lesson, you were introduced to a new concept, namely linear combination. I said that this concept linear combination is a basic notion in the subject linear algebra, and it plays an important role in the further studies of this subject. For better understanding of the concept linear combination, let us go through some examples. The first example is some linear combinations of a single vector a bar are 1 by 2 a bar minus 2 by 3 a bar 3 a bar minus a bar etc., which are all scalar multiples of a bar. If you notice here, I am taking a single vector and saying that all these are considered as linear combinations. While defining the concept linear combination, or even when I have introduced that concept to you, I have taken two vectors and more than two vectors to get that concept linear combination. But here, while giving example, I am taking a single vector and scalar multiples of that single vector. I am treating them as linear combinations. Yes, this can happen because all the scalar multiples of a bar are nothing but the linear combination of that vector itself. So even though we are not taking sum of linear scalar multiples of a bar, each single scalar multiple of a bar can make a linear combination of that vector a bar. And in all the examples I am going to give, I want to give the geometrical interpretation for each of the examples. So in this example, let us see what is the geometrical purview of the single vector linear combinations. So the above linear combinations of the single vector a bar, which are half 1 by 2 a bar, half a bar or a half a bar, minus 2 by 3 a bar, 3 a bar, comma minus a bar. How can we look all these geometrically? I am saying that these all are vectors lying on a single line. How is it possible? Let us see now. Let O a bar is equal to a bar be any vector in real numbers, then it will be on the real line. So O a bar I have taken as a bar and I am representing it a vector from O to A. Now 1 by 2 a bar, 2 by 3 minus 2 by 3 a bar, 3 a bar, comma minus a bar, etc. are all multiples of a bar. They all lie on the same line, which consists of the vector a bar. See here in the diagram, I have taken a real line, which is a horizontal line. On that, the vector O a bar is origin and O a is represented as a bar. I have shown you the OA is equal to a bar in this figure, and OB is a vector which is 1 by 2 of a bar. That means the vector OB has half the magnitude of OA and will have the same direction. Of course, I have not mentioned the directions in this diagram. Still, we have to understand the directions by the vectors OA, OB, which denote that the vector starts from O and ends at A, and that will be the direction of that vector. So OA is A bar and OB is half of A bar, means it has half the magnitude of A bar and will have same direction. And OC is another vector which is 3 times of A bar. The scalar multiple of A bar by number 3 is the vector denoted as OC in this figure, and we can see OC is 3 times the magnitude of OA and in the same direction as OA. And on the left hand side of origin we can see two vectors OD and OE. OD is minus 2/3 of A bar. As it is in minus sign, it is on the left hand side of origin. It is 2/3 of A bar, means 2/3 magnitude of A bar, and so it is in length less than the vector OA. And finally the vector OE is minus A bar, which is on the left hand side of origin where it has minus sign. We can also see that it has same magnitude as OA, but it has opposite direction. OA is in opposite direction to OE with the same magnitude. So that is how on a single line, that is on a real line, we can see all the scalar multiples of A bar including itself. So this is the geometric interpretation of the scalar multiples of A bar, which we are viewing as linear combinations. Now let us move on to the next example. Okay, before moving to the next example, I want to give you some note point also. If A bar is equal to 0 bar, already we are taking a single vector. Even that itself is a 0 vector. Then what will be its linear combination? So 0 bar is equal to 0 A bar is the linear combination of A bar when A bar is 0 bar. Even then, even for a 0 vector, we can find the linear combinations with multiples 0 for A bar. So 0 A bar is a linear combination of A bar which is equal to the 0 vector. Now moving on to the next example, some linear combinations of any two vectors v1 bar comma v2 bar. I am taking them as 1 by 2 v1 bar plus v2 bar comma minus v1 plus 2 v2 comma root 3 v1 minus v2 minus 2 v1 comma minus 3 by 2 v2 etc. which are any vectors again. All these are v1 plus v2, half v1 plus v2 etc. are again vectors. So how can we justify 2v1 is sum of the vectors v1 and v2? It is a linear combination of v1 and v2. It can be expressed as 2v1 plus 0v2. Then we can see both the vectors v1 and v2 in it, even though it is 2v1. In the same manner, minus 3 by 2 v2 can be expressed as 0v1 plus minus 3 by 2 v2, so that it is also a linear combination of the vectors v1 and v2. Now going to the geometrical interpretation of this example, consider the two vectors v1 v2 in the figure like this. It is in the xy plane. They are in the xy plane. v1 in the second quadrant, v2 shown in the first quadrant. So if these two vectors are in like this, positioned like this, how all the scalar multiples, sum of scalar multiples of these two vectors, which I said are linear combinations of the vectors v1, v2, can be represented in the xy plane that we have to see now. So the first vector is, the first linear combination is 1 by 2 v1 plus v2. So such linear combinations, how can we see in this figure? Let us see. Geometrically, the linear combinations of v1 and v2 can be any point in the plane as shown in this figure. What is that point and how can we identify them? See, I have taken the v2 in first quadrant and v1 in the second quadrant as shown above. Now I am taking parallel lines to both of these vectors in such a manner that every parallel line to v1, the vector v1, is on both and either side of the vector v1 at a distance or at a length of the vector v2 on both sides of v1. So every parallel line to v1 is on either side of v1 at a distance of v2 on either side. So if you keep on maintaining the distance v2 on either side of v1, get extending like that, we can get so many parallel lines. And in the same manner for the vector v2 also, at a distance of the vector v1, at a distance v1, we can get so many parallel lines on either side of v2. And as they all of them are in xy plane, they all are intersecting, and each intersecting point gives, when connected to origin, gives rise to some linear combination of these two vectors v1 and v2. Not only the positive sums, we can even have the negative sums as linear combinations which are made of these two vectors. How? Let us see about the negatives of these two vectors. The negative vector of v1, when v1 is in second quadrant, that lies in the fourth quadrant. The negative will lie in the fourth quadrant, and that will have the same magnitude but will have opposite direction as shown in this figure. In the same manner, as v2 is in first quadrant, the negative of it, minus v2, is in third quadrant, and we can see that the whatever be the points, intersecting points that are lying in second quadrant and third quadrant, even in fourth quadrant, have negative scalar multiples of v1 bar or v2 bar, or both of them, and so that when added to other scalar multiple, they will give rise to different linear combinations. So in that way we can see all these linear combinations in this diagram. So 1 by 2 v1 plus v2 minus v1 plus 2 v2 root 3 v1 minus v2 etc. all are some linear combinations which are identified by some intersecting points, or some points may not be intersecting points, they will lie on that parallel lines or somewhere in the xy plane. So this is how, and the scalar multiples of v1 and the scalar multiples of v2 lie on the lines where v1 and v2 are lying. So that is how on the line v1 we can see the positive side 2v1, 3v1, so on, and the negative side minus v1, minus 2v1, minus 3v1, so on the same line. And similarly for v2, 2v2, 3v2, so on are on the positive side, they are the scalar multiples of v2, and on the negative side minus 2v2, minus 3v2, so on are the scalar multiples of it. Not only the intersecting points, but each and every point in this xy plane is a linear combination of these two vectors v1 and v2. And vice versa also. That means conversely, each point in this xy plane gives rise to a linear combination of the vectors v1 and v2. So we can understand that every point is a linear combination in this xy plane. So this leads us to understand that any point in the plane can be expressed as a linear combination of v1 bar and v2 bar, and conversely every linear combination of v1 bar and v2 bar can be identified as a point in the plane. Thus, the set of all linear combinations of two vectors v1 bar and v2 bar forms the plane containing v1 bar and v2 bar. Also, the origin which denotes the 0 vector 0 bar is also a linear combination of the vectors v1 bar and v2 bar. For 0 bar can be expressed as 0 bar is equal to 0 v1 bar plus 0 v2 bar. Now there is a problem based on linear combination. If v1 bar is equal to 1 0 minus 2, v2 bar is equal to minus 4 3 8, v3 bar is equal to 2 5 minus 4, determine whether b bar, this is some other vector, is a linear combination of v1 bar, v2 bar, v3 bar or not. So we are given three vectors and we are asked to find whether another vector b bar is a linear combination of these three vectors v1, v2, v3 or not. So let us see how can we do that. So the given vectors I have mentioned in the beginning as they are, and next I am taking b bar as linear combination of these vectors. Linear combination means sum of scalar multiples of these three vectors. So that is equal, that we can take here as b bar is equal to c1 v1 bar plus c2 v2 bar plus c3 v3 bar, where c1 c2 c3 are scalars or we call them as weights in the context of linear algebra. So c1 v1 bar c2 v2 bar plus c3 v3 bar is equal to b bar when we substitute all the vectors v1 v2 v3 in this, and even b bar on the right hand side that looks like this, and on the left hand side we can have the scalar multiplications and then adding those vectors by addition of vectors, using addition of vectors, and we can get this vector on the left hand, single vector on the left hand side, which is c1 minus 4c2 plus 2c3. The next row is 0 plus 3c2 plus 5c3, and the last row is minus 2c1 plus 8c2 minus 4c3. By recall the equality of matrices, as these two vectors are nothing but the matrices of the order 3 by 1, as they are of equal order, and we can compare or we can equate the corresponding elements in both of them and get these equations. So we got three equations by equating on either side of the above two vectors, and this system I am representing as equation number 2. B bar is equal to c1 v1 plus c2 v2 plus c3 v3 when substituted the vectors all of them. I am treating it as equation number 1. Now b bar will be a linear combination. Our aim is to see that whether b bar is a linear combination of v1 v2 v3 or not. For this, if we can understand this by the remark that if c1 c2 c3 have some numbers, or even if they have 0, all of them being 0, that can also be considered as a solution, or c1 c2 c3 having unique solution can also be considered as a solution. And infinite numbers of values for C1, C2, C3 can also be considered as a solution. But there is another option also where the values for real values for C1, C2, C3 may not exist at all. So that is also there, which when we say that the system is inconsistent and has no solution. So our aim is now to see that whether C1, C2, C3 are some numbers, may be finite or infinite, or they do not exist at all. Let us see now. So let the above system, which is represented in equation 2, in matrix form, by matrix equation we can represent it as Ax bar is equal to B bar. So this is how the matrices help us to make the system of linear equations to a simpler form. So the whole system which is in equation 2 can be written in this single equation, such a simple equation Ax bar is equal to B bar, which is a matrix equation. In this, capital A is the coefficient matrix which is shown here like this. A is equal to 1 minus 4 2 0 3 5 minus 2 8 minus 4, which are the coefficients of V1, V2, V3 in the system in 2. X bar is the variable matrix. It is a 3 by 1 column vector given like this. X bar is equal to x1, x2, x3. And B bar takes the values in the right hand side of those equations. Now consider the augmented matrix AB bar. AB bar has first three rows and columns taken from A, and the last column is replaced by the values in the vector B bar. Now this augmented matrix using elementary operations, some elementary operations can be changed into echelon form. The echelon form you have introduced in the, you have recalled in the prerequisites. Now applying the row elementary operation R3 as R3 plus 2 R1 in for the row R3 in the augmented matrix, we can see the resultant matrix as 1 minus 4 2 3 0 3 5 minus 7 0 0 0 3, in which the last row is consisting of 3 zeros and a non-zero number at the end. So this gives the conclusion that by your previous knowledge you can recall, when the last row in the augmented matrix is 3 zeros and a non-zero number, then the system of equations which we have considered will be inconsistent and has no solution at all. And by that, here we can say the last row elements are all non-zero except the last element, and hence the system of equations in 2 is inconsistent and has no solution. Hence there exists no scalars. No solution means the values for C1, C2, C3 cannot be found as in real, cannot be found as real numbers or in R. So hence there exists no scalar C1, C2, C3 satisfying equation 1. That is, B bar cannot be expressed as a linear combination of V1 bar, V2 bar and V3 bar. So they have asked to determine whether B bar is a linear combination of V1, V2, V3 or not. So our answer is B bar cannot be expressed as a linear combination of V1 bar, V2 bar and V3 bar. So with this, I will sign off this video lesson now. Go through the lesson properly and make the concepts well understood by you. Thank you.